Hey guys, how you doing? It's Mr. Lee with a quick video on Chapter 7. Today we're going to look at Chapter 7, which is random variables. I know you guys started this chapter already. Chapter 7 is not like, it's not super heavy with like really hard concepts or really difficult procedures or anything like that. The math is actually super light, very, very simple. And the concepts are pretty intuitive as well. And there's not too many of them. So we actually have a reminder. We've combined chapter 7 and chapter 8. So I shouldn't say we combined them, but the assessment that you're going to have is on both chapter 7 and 8 together. Okay, we're not going to have a separate chapter 7 assessment and a separate chapter 8 assessment. Okay, and those will be the last chapters that we cover in semester 1. So in semester 1, your first semester final will cover chapter 1 through chapter 8. Okay. Okay, so random variables. So random variables are not like variables in Algebra 1, where it's little x, little y, little z. An unknown in Algebra 1 or in geometry is just a variable is just an unknown. It's just something you solve for. Random variables are different, and there's two types of random variables. There's both discrete and continuous random variables. So today I'm going to lecture on 7.1 and 7.2. Again, they're very short and they're very light, and so I'm just going to combine them. And then in the next lecture, I'll talk about 8.1 and 8.2, which is the binomial random variables and geometric random variables. But today we're going to talk about discrete and continuous, differentiate between those two, and then figure out how to calculate the mean and the variance of discrete random variables. So this is where we're heading. Okay, so we learned in chapter 6 what a probability model is, and a probability model describes all the outcomes of a chance process and the associated probabilities of each one of those outcomes. A numerical variable that describes the outcomes of a chance process is now called a random variable. So a random variable in statistics, first of all, it's the outcomes of a chance process. That's where the chance process is the random, and the outcomes is the variable, because there's more than one outcome, right? The outcome can vary. There's more than one. Okay, so the probability model for a random variable is just the probability distribution. Okay, so probability distribution is specific to a random variable, and it's basically just the same thing as what we learned in chapter 6 with a probability model. It is the probability model for the outcomes of that variable. Okay, so if we think about like tossing a fair coin 3 times, okay, well, what are the different values that can come out? Well, first we have to define what our random variable is. What is the outcome of interest? Well, let's say that heads is how we define capital X. And notice that with random variables, we're going to use capital letters, and that's to distinguish them between like algebraic variables, little x, little y, little z. We're going to use capital X, capital Y, capital Z, that kind of thing with random variables. Okay. So what are the different things that can happen if you toss a coin 3 times? Well, if we're looking for heads, so we're going to define capital X as the number of heads obtained. Well, when you toss the coin 3 times, either you can get 0 heads, or you can get 1 or 2 or 3. Okay. And what are the associated probabilities? Well, you have to think about all the different outcomes, right? So to get 0, a value of 0, x equals 0, that would mean that you got tail, 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 right? To get a value of 1, that means, well, there's different ways you could have gotten 1. You could have gotten, the head on the very first toss. So it could be HTT, it could be THT, tail, then a head, then a tail, or it could be TTH, where the head came on the very last coin toss, right? And same thing with 2, and same thing with 3. So there's all the different outcomes, and there's all the different ways you can get 0, 1, 2, or 3. So there's 8 possible outcomes. Okay, so our random variable X, okay, has values of 0, 1, 2, or 3, and then the probability associated with those values is 1/8, 3/8, 3/8, and 1/8. Take a moment to just kind of digest that, to think about that, and then also notice that you can plot this on a histogram. Okay, so now we're going to distinguish between discrete and continuous. And a lot of you know the difference between discrete and continuous values. You've learned this in previous math classes. Discrete are like you can count them because it's like a particular value, particular value, particular value. Whereas continuous, there's like a whole range of values or a whole interval of values, and it contains every like value between those two values. Like if you think about like the continuous values between 0 and 1, how many are there? Well, there's infinitely many continuous values between 0 and 1 on a continuous scale, right? Because between 0 and 1, well, there's 0.5, there's 0.1, there's 0.01, 0.001, 0.0001, et cetera, et cetera. So it's infinite. But if we're on a discrete scale, if we look at the numbers 0 and 1, we're either on 0 or we're on 1. Okay, so that's the difference between discrete and continuous. As it relates to random variables, first we're going to start with discrete random variables. So discrete random variables has a set number of possible outcomes. Okay, there's a set number of values. Okay, you can count how many values there are. Okay, whereas with continuous, it's infinitely many, so you can't count them, right? So here are the different values. Remember in our tossing the coin 3 times, these were 0, 1, 2, 3. Those were the possible values. And then we have their associated probabilities or their corresponding probabilities, right? So X sub 1 has a probability of P sub 1, X sub 2, et cetera, et cetera. Okay. And notice this looks just like a probability model, which it is. And in this case, it's also called the probability distribution of the random variable capital X. Okay. Notice that capital X, we use capital X as the notation for the random variable. And then the values are the lowercase x with the sub. Okay, sub 1, sub 2, sub 3. Okay. These are rules that we already know. Each one of these, P1, P2, P3, these have to be values, valid probabilities. So between 0 and positive 1, you can't have any negative numbers, no numbers greater than 1. Okay, then the sum of all of these has to equal 1. Okay, because remember we talked about the sample space, right? Okay, so there's an example called of a scale called the APGAR scale. Okay, and when babies are newborn, hospitals in America use this APGAR scale, and they measure like the weight, the height, the length. There's a couple other things. I don't remember everything. I've been through this 4 times with my 4 kids, and we got APGAR scores for all of them. But the APGAR score basically is an indication of, it's like a metric of like how quote unquote healthy is that baby, compared to the population of all newborn babies, right? And so there's a scale from 0 to 10. So is this discrete or continuous? Well, this is discrete because either you get a score of 0 or 1 or 2 or 3. There's no like 2.2, 3.5, something like. No, it's just those values. And then here are the corresponding probabilities for each one of those APGAR scores. Okay, so the higher the probability, the sort of larger and heavier and like just the bigger the score is, the quote unquote healthier the baby is, okay, as it's newborn. Okay. So A, B, and C show that the probability distribution for X is legitimate. So remember, there's 2 things you're going to check there. First of all, every one of these probabilities is legitimate. Okay, it's valid. It's between 0 and 1. Okay, no negative numbers, no numbers greater than 1. Then all of these probabilities have to add up to 1.0. And yes, they do. So A is good. Okay, B, make a histogram of the probability distribution. Describe what you see. Okay, remember when you're describing a histogram, okay, what you're talking about are the SOCs, right? The shape, center, spread, and outliers, right? Shape, center, spread, and outliers. So here we go. Here's our histogram. Okay, shape is unimodal. Okay, it's also skewed, pretty heavily skewed to the left. The center is somewhere between 8 and 9. We have a mode at 9. We would guess that the mean is somewhere, pulled to the left. So somewhere maybe 8 point something. Okay. Spread, we would talk about IQR or standard deviation. We don't have any of the summary statistics here, so we're not really going to talk too much about the spread. And then finally, we have shape, center, spread, and outliers. We don't know. Okay, we haven't calculated the IQR or anything like that, but we're going to guess maybe possible outliers at 0 and 1 here. Okay, possibly. okay, or 1 and 2, 0, 1, and 2. Okay. So part B, APGAR scores of 7 or higher indicate a healthy baby. What is the probability that capital X, remember it has to be capital because random variables are capital. What's the probability that capital X is greater than or equal to 7? Well, you just add 7, 8, 9, and 10. The probability of 7 plus probability of 8 plus probability of 9 plus probability of 10. You just add those 4 values. Okay, and then you get 0.908. So how do you interpret this in context? Okay, we have approximately a 90.8% chance of randomly choosing a healthy baby. Okay, in other words, like if we randomly select a baby out of the population of all newborn babies, okay, chances are, the probability is approximately 0.908 that this baby is going to be considered healthy according to its APGAR score. Okay. Okay, so how do you find the mean of a discrete random variable? Well, the mean is also called the expected value, okay? And so the expected value is E of X, okay? And it turns out that all you have to do is to find the mean is just to multiply each value by its weight or by its probability. Okay, so P1 times X1 plus P2 times X2 plus P3 times X3 all the way down. Okay, because if you think about what an average is, okay, or a mean is, it's just a weighted average, right? It's just a weighted average. So here we literally have the weights. We have the weights to the values. So all you have to do is just multiply this times that, plus this times that, plus this times that, plus this times that, and then you get a mean at the end. Okay, that is also called the expected value. So one way to think about the expected value is another way to word the expected value would be like knowing what the probability distribution is right here, okay, if we randomly select a baby out of the population of all babies, what is the expected APGAR score for this baby? What's the expected value? Now, couple things about expected value. First of all, it's super simple to calculate, just this times that plus this times that plus this times that, et cetera, et cetera, okay? But a couple things you have to note. The mean or the expected value does not have to be one of these values. Okay? And it's not going to be. It's going to be a value between these two values. The other thing is that it does not have to be an integer value. Okay. So when you do that calculation on your calculator, okay, you're going to find that the mean of that distribution is actually 8.128. Sorry about the messed up slide. It just got, degraded somehow. But when you do this, okay, this times this plus this times this plus this times this plus this times this, et cetera, you're going to get a mean of, or an expected value of approximately 8.128, okay? Okay, so now how do you calculate standard deviation? Remember that the standard deviation is just the square root of the variance, okay? It's square root of the variance. So how do you calculate the variance? You just simply take each one of these values, okay? So X sub 1, see how far away that is from the mean of the entire distribution. So X sub 1 minus the mean, so that's called the difference, right? And then just square that difference and then multiply it by the weight of that value, okay? So X sub 1 minus mu, okay, and then square that difference and then multiply that times P sub 1, okay, and then just do that for all of the values and you get variance or sigma squared, okay, you get sigma squared. Then how do you get standard deviation from sigma squared? You just take the square root of it, okay, and so let's go ahead and do that for this particular problem, okay. So we just take each value, 0 minus the mean, square it, and then multiply it by the weight or the probability. Okay, do that for each one of these 11 values. Okay, and then what do you get? You get the variance. The variance is sigma squared x is 2.065616. Then you just take the square root, okay, caret 0.5, okay, and you get approximately 1.437 for your standard deviation. Okay. So this entire probability distribution has an expected value of 8.128 with a standard deviation of 1.437. Now, how are you going to interpret this 1.437 in context? That means out of the population of all newborn babies, right? If we look at all the newborn babies, okay, we expect like one of those newborn babies, we expect the newborn baby to have an APGAR score value of 8.128. okay? But we also know that, okay, that randomly selected babies, APGAR score is going to be approximately, on average, 1.437 units away from 8.128. Okay, so on average, randomly selected babies' APGAR score will differ from the mean of 8.128 by about 1.4 units. All right, last thing, we got to talk about continuous random variables. So continuous scale versus discrete scale, right? So continuous scale, if you look at all the numbers between 0 and 1, there's an infinite number of numbers between 0 and 1, right? So what's a continuous random variable? Well, a continuous random variable, x, takes on all the values within an interval. Okay, this is the key, it's within an interval. So you have to define the interval. You have to define, well, what is the lower bound and what is the upper bound for that interval? Okay, and then how do we calculate, well, what's the probability of an interval? Okay, calculus students, you guys are going crazy with this. You already know the answer to this. But specifically in terms of AP statistics, we talked about density curves. Remember way back in chapter 3 when we were talking about the normal model and the standard normal model. Okay, we talked about density curves. Well, there's definitely going to be just some density. I was looking at the homework problems. There's definitely some weird shaped density curve problems in this chapter in the homework. So you can expect that on the test as well. Okay. But density curves, okay. Probability of any event is the area under the density curve and above the values of x that make up the event. So again, we have an interval that we're going to be looking at. So the probability model, again, it's going to be 0 and 1. Okay, but here's something very important to write in your notes. Okay, a continuous random variable x or a continuous random variable y has infinitely many possible values. All continuous write this in your notes. All continuous probability models assign probability of 0 to each individual outcome. Only intervals of values have positive probability. So what does that mean? That means if we're in the setting of a continuous random variable, not discrete, but continuous random variable, if you want to know what is the probability of one singular outcome, that's 0. You're never going to have one singular, you're going to have a range or what's called an interval, okay? And you're going to calculate the area of the interval. Thinking of this geometrically, if you recall what, the normal model looked like, but if you recall really any density curve, it could be skewed left, okay? What is the area under the curve of one point? Okay, calculus students, you already know this. Geometry students, those of you that took geometry, think about the area of one point. Okay, it's 0. It's 0. Okay, and technically it wouldn't be a point, it would be a line segment. But again, a line segment is one-dimensional. It has no area because area is a two-dimensional measurement. So the two-dimensional measurement of a one-dimensional shape is 0. It's not defined. You don't have a two-dimensional measurement. Okay. So this is an important point to recall. And let me go ahead and show you what this looks like, okay? So now, remember when we were talking about normal distributions way back in chapter 3, I said, well, there's a couple different things that generally are normally distributed. One of those things is sort of like biological phenomena, right? So there's an example in the new textbook about young women's heights. And we find that if we take the population of all young women, okay, we can find that their distribution is a continuous random variable. Okay, it's a continuous random variable y. And the probability distribution is normal. It's a normal distribution with a mean of 64 inches and a standard deviation of 2.7. So our question of interest is what's the probability that a randomly chosen young woman has a height between 68 to 70 inches? Okay, there's your interval. 68 is your lower bound, 70 is your upper bound. Okay, those of you that are really focused on calculator procedures, you're already thinking normal CDF. Here's my lower bound, here's my upper bound, here's my mean, here's my mu, here's my sigma, right? And you're correct, okay? But technically how we teach that is, let's go ahead and graph. Okay, let's draw the diagram of the entire distribution. Okay, and the mean is 64, 2.7, 2.7. So here's our interval of interest. What is the probability that X, okay, or in our case, capital Y is between 68 and 70. So that's a compound inequality. Okay, what is the probability that 68 is less than or equal to Y is less than or equal to 70? Well, how did we do this? Way back in chapter 3, we standardized first. So we got the z-scores for 68 and 70. So on the standard normal, 68 is just 68 minus 64 over 2.7, so 1.48 standard deviations right of the mean. 70, when we standardize that, that is 2.22 standard deviations to the right of the mean. So the interval of interest is just this shaded region. So our compound probability statement is, what's the probability that 1.48 is less than or equal to z is less than or equal to 2.22? Right, so right here. And then how did we do this in the using table A? Well, table A only gives us left tail probabilities or left tail densities or left tail areas. So we simply take the left tail area of this greater one, and we subtract the left tail area of that, and that leaves us the shaded region. Okay, and so looking in table A, there's those values. And so our region of interest has an area of approximately 0.0562. So now how do we interpret that 0.0562 in the context of this problem? Literally repeat verbatim the words of the question. So instead of saying what is, just drop that and just write it as a statement. The probability that a randomly chosen young woman has a height between 60 and 70 inches is 0.0562. Okay. Another way of interpreting this is there is about a 5.6% chance that a randomly chosen young woman has a height between 68 and 70 inches. All right, guys, hope you enjoyed the video. If you have questions, post them in the discussion board and have a great break. Notice that there is quite a bit of homework that you need to work on over the break. That is why you're getting time in class to work on your homework. Okay, so enjoy the homework, enjoy your break, and I will see you when we get back from break. Thanks, guys.